And welcome to TI Precision Labs. In this video, we're going to discuss eye diagrams and bathtub curves as key electrical measurements in high-speed signaling environments. Bathtub curves can be useful in evaluating your system's performance over different amounts of data and the probability of bit errors occurring over a set amount of data. In this session, we're going to discuss the fundamental elements of a bathtub curve, how bathtub curves relate to eye diagrams, and how they are used to evaluate system performance before PCB fabrication. In order to begin the discussion on bathtub curves, mainly their construction and utility, we start with the eye diagram. An eye diagram is a data-dependent electrical measurement used to evaluate high-speed transmitter and receiver performance. Two key measurements included in the eye diagram are total jitter and eye width. Reference the image on the screen as a brief refresher on where these items are located. Eye diagrams are great when trying to understand how data is affected by a certain channel. However, eye diagrams only show the data quality over a relatively small data sample used to construct the eye diagram. Systems transmitting data with high total jitter and small eye width tend to have poor performance and are more likely to include erroneous bits. The eye opening can be used to extract an estimate for bit error rate, or BER, for the specific eye diagram and form the bathtub curve. For more background on eye diagrams, please refer to our TI Precision Labs video, What is an Eye Diagram? Bit error rate is useful in discussing the overall fidelity of a given data link. BER describes the probability of bit errors occurring over a set amount of data. Bit error rate is calculated by dividing the number of bit errors by the total amount of bits being measured. BER is expressed in scientific notation where only one bit error is allowed for the total number of bits measured. This unitless number is often used to describe the amount of data included in a particular measurement without error or at most one bit error. In system-level validation, it can be useful to understand how different amounts of data are affected by a given channel, especially at the intersection of total jitter and BER. Initially, it may be useful to think about total jitter as a single measurement of the amount of timing variation we have in the eye diagram, as we have seen previously. However, total jitter, or TJ, is the sum of two components, all the deterministic jitter, DJ, and random jitter, RJ. Each edge in the data pattern may see a slightly different amount of timing variation due to the different components of TJ. Each edge, even in the same frequency range, may not vary by a single amount due to the RJ component of TJ. This means that TJ is more statistical in nature and is better represented by a histogram called the TJ probability density function F. For more background on total jitter and its components, please refer to our Precision Labs video, What is a Signal Conditioner? Due to the unbounded nature of RJ, caused by thermal or shot noise and other unbounded sources, the impact of RJ depends on sample size. This causes the peak-to-peak value to grow without bound over time. Taking this into account, TJ will continue to grow as more and more data is included in the measurement. You can see a simplified TJ PDF example above. Now you may ask, why does total jitter matter in this discussion on bathtub curves? Shortly, you will see an example of the impact total jitter has on the bathtub curves themselves. A bathtub curve is a simple yet elegant tool in visualizing how large amounts of data running continuously through a transmission media can affect your system performance. The bathtub is a graphical way to look at the eye diagram statistics in terms of BER versus time across the eye at the zero crossing of an eye diagram. You can notice that the y-axis of the bathtub curve shows the BER in a unique way. Most commonly, it is expressed as the component of the calculated BER. Using the bathtub curve, it allows the user to understand what level of fidelity is achieved in the system across larger and larger chunks of data. An ideal bathtub curve can be seen above. Remember that BER only describes the probability of bit errors occurring over a set amount of data. However, it is crucial to understand the link's fidelity in this way. In many data streams, like video or audio, or data streaming from a sensor, one bit error can result in data corruption. Corrupted data can result in a wide variety of system failures. A very low BER is achieved within the area noted by the green arrow. This area indicates where bits are considered valid from a timing perspective, similar to the negative space of an eye mask. The yellow arrow here indicates the minimum timing requirement for the data in question. While not naturally a part of the bathtub curve, keeping these two arrows in mind for the calculated result can be useful in understanding the bathtub curve. To create a bathtub curve, most engineers will characterize the eye to a level of 10 to the negative 6 to 10 to the negative 9, extract the TJ PDF with its components, then extrapolate, using simulation or other calculation tools, to t to the negative 12 and beyond. Now let's look at a more realistic example. In this example, we have a simple setup with a 10 gigabits per second transmitter connected to a 10 gigabits per second receiver by a 5-inch long, 4 mm wide, differentially coupled FR4 strip line. Above, you can see the associated eye diagram with an eye mask showing the requirements for timing in this example. The eye diagram above is composed of 10 to the 6 bits using a mask defined based on a BER of e to the negative 12. Here you can see the result of bathtub curve calculations on the right and the associated eye diagram on the left. Depicted by the green arrow, you can see the corresponding eye width in both the eye diagram and bathtub curve. In the bathtub curve, you can see the achieved BER of 10 to the negative 6, or negative 6 on the y-axis. Since the measured eye width here is larger than the minimum bit timing, bit errors are not likely due to jitter. However, if we consider a lower BER, or more data is introduced into our measurement, the achievable BER decreases until the calculated eye width violates the minimum bit time. This is depicted by the yellow arrow. This means at this point and beyond, bit errors can be caused by accumulated jitter. In this example on the right, you can see that this point occurs at a BER of e to the negative 10, or negative 10 on the y-axis. In designs that implement high-speed protocols like USB 3 and PCIe Gen 5, where the eye width must be acceptable at a BER of e to the negative 12, this example is not acceptable. It is also important to know standards like PCIe and USB typically have a targeted BER of e to the negative 12 or better. In most cases, and the examples above, the mask is defined based on a BER of e to the negative 12. If the BER of e to the negative 10 is not sufficient for your design, we can add a signal conditioner, like a redriver, to improve the result. Looking above, we have added a redriver 4 inches from the transmitter and 1 inch away from the receiver. In the bathtub curve, we can see the improvement in the eye width at e to the negative 10, and it allows the system to reach a BER of e to the negative 12. Also, adding the signal conditioner moves the system limitations down to e to the negative 14, where the eye width violates the minimum bit timing. Redriver placement can also impact these results. Using bathtub curves helps to validate system robustness to jitter. During initial evaluation of your design, an eye only at a BER of 10 to the negative 3 may look nice, but it does not correctly represent the amount of data that will run through your transmission media regularly. Further investigation and stress testing may result in a high number of bit errors after PCB fabrication. It is important to understand your system's BER requirements and evaluate the signal performance accordingly. To see an example of this, compare the eye diagrams at 10 to the negative 3 and 10 to the negative 6 BER levels above. See the eye width reduction as more data is included in the measurement.